Okay, so today I thought it'd be useful to talk to you about the technique that I specialize in, which is NanoSIMS. It's not a technique that is very widely known. There's actually only 50 of these instruments worldwide. So I want to talk to you today about how we've been using the NanoSIMS to look at deuterium in various different metals at microstructurally relevant scales to understand where hydrogen is being accumulated in these metals. So because this technique is not very well known, I thought it'd be useful to spend a little bit of time at the start talking about how the technique works. Seems to be advancing by itself. So the technique is based on the principle of secondary ion mass spectrometry, or SIMS. And with this technique, we use a charge-focused primary ion beam to bombard the sample surface. And this bombardment results in sputtering or removal of the top few atomic layers of the sample surface. And what we can do is we can collect the secondary ions that are emitted during that process and send them into a mass spectrometer, allowing us to determine what they are in terms of which elements. And by scanning this primary ion beam over the sample surface, we can build up a chemical map of the elemental distributions contained within our sample. And you can also see that this is a very surface-sensitive technique. We're only looking at the top few atomic layers of our sample surface. So this is just a very simple schematic of the NanoSIMS instrument. We have two ion beams on the sample surface. We've got a cesium ion beam and an oxygen ion beam, which we focus down onto our sample. We scan the ion beam over the sample, and we collect the secondary ions that come off the sample surface. In the NanoSIMS, we send them into a magnetic field, which allows us to separate out those ions according to their mass. And from that, we can then build up chemical images of our sample surface. So here is what the machine looks like at the University of Manchester. It's quite a large-scale instrument. We have our two ion sources at the top of the instrument here. We have the sample sitting in this chamber here. Here is the magnet at the back, and we have our detectors sitting along this part here. So why might you want to use NanoSIMS? For various different applications, and also specifically looking for hydrogen in metals. So the NanoSIMS offers high lateral resolution. We can actually focus that primary ion beam down to 50 nanometers. Although routinely, due to trade-offs between lateral resolution and sensitivity, we may be looking at somewhere between 100 and 200 nanometer spatial resolution. So that's much better spatial resolution for chemical mapping than you can get, say, in an SEM with EDX. The NanoSIMS can offer high sensitivity, so we can look at trace element distributions. So we can look at parts per million level concentrations for some elements. So again, much better than SEM and EDX. The high mass resolution that allows us to distinguish between elemental species that have nominally the same mass. So for example, sulfur has a mass of 32. Two oxygen atoms bonded together also have a mass of 32, but we can distinguish between them. And that's really important when we're doing isotope work that I'm going to show you today. We have 7 detectors, so we can simultaneously detect 7 ionic species. So we can co-locate our element of interest with something that tells us about the morphology of our sample. So we can know exactly where in the microstructure or any particular structure where that element is located. And the key thing for this talk here is that the NanoSIMS can actually detect almost all elements in the periodic table. And that is right through from hydrogen all the way through to uranium. So there's very few techniques that actually can detect light elements such as hydrogen, lithium, and boron. The NanoSIMS is really good at that. And as I mentioned, we can detect isotopes. This is a mass spectrometry technique. So we can actually utilize this to be able to artificially introduce isotopes into our sample and track where they are going. So some commonly used isotopes are listed here. And in this presentation, I'm going to focus on deuterium especially, and also oxygen-18 and how we have utilized that. Now, I like to include this slide just to preempt some questions that I typically get at the end of my talk. The NanoSIMS is not perfect, and there are certain things we can't do with it. So it is difficult to detect some elements, namely things like cadmium and zinc, and that's simply because we just don't get enough secondary ions from these elements. It's not a technique to map over large areas. This is very time consuming. So the NanoSIMS really is a technique for looking at small regions at high spatial resolution. It doesn't give you any chemical state information or molecular information, so you can't tell so much about the bonding. It's basically elemental and isotopic information that we're getting. Especially important here for the hydrogen work, quantification is incredibly difficult with SIMS. So I can't tell you exactly what percent of a particular compound we have in a certain region, but we can look at relative differences between samples. There is no cryo stage on the NanoSIMS. We're doing everything at atmospheric temperature. Again, when we talk about hydrogen work, hydrogen is incredibly mobile in materials, and so this is potentially a real disadvantage for this work. But I'll show you how we've actually think this is not so much of an issue. But if you were to look at biological samples, for example, then that is potentially a real issue because we're operating under ultra-high vacuum. I've put in brackets at the end that this is a destructive technique. So you are actually destroying your sample as you analyze it. So you simply can't go back and analyze the same region again because it will have gone during your analysis. So if you want to do any kind of correlative work, you need to make sure you do all the other techniques first before you come to the NanoSIMS. So what I want to focus on today is how we've been using the NanoSIMS to look at hydrogen embrittlement. So I'm hoping that most of you will be familiar with this, but just as a quick summary, when you have hydrogen inside your metals, for example, you often get a reduction in toughness and load-bearing capacity of those metals. And what you can get is cracking and catastrophic failure of that material at a much lower yield stress than expected. And we can see that in this graph here, the effect of without hydrogen, this nickel alloy would fail at this point. But as soon as you have hydrogen into that material, it fails much earlier than expected. And you can see the difference here in the fracture surface as well, brittle versus ductile failure. So a lot is still unknown about where the hydrogen is going in these metals. So the aim of this project was to try and be able to identify where hydrogen is being trapped inside the microstructure, in this case of steel alloys, nickel alloys, and zirconium alloys, by looking at the hydrogen distribution at high resolution using the NanoSIMS. So there are a lot of issues associated with hydrogen detection. That's one of the reasons why there's not actually that much out in the literature about where the hydrogen is localized in these metals. We have a lot of bulk techniques, but there are actually very few techniques even capable of detecting hydrogen in the first place, let alone localizing it to very specific features in the microstructure. And furthermore, there's always a little bit of ambiguity regarding the origin of the hydrogen that we actually detect. So did that hydrogen come from the experiment, the hydrogen that we put in there during charging, for example, electrochemical charging, or did it come from the vacuum system? That's particularly important in these high vacuum instruments such as the NanoSIMS, sample preparation with polishing and grinding in water, for example, or even just storage of these samples, is it picking up hydrogen? So that's where isotopes come into play. So it's an example here of a zirconium alloy that we're looking at in cross-section. So here is the hydrogen image from the NanoSIMS. Over here, this dark region on this side here is resin that we use to just mount the sample. Here we have a thin oxide layer on this zirconium alloy, and here we have the bulk metal. Now, zirconium alloys very often have hydrides contained within them, and we can clearly see a layer of hydrides along here in this hydrogen image. So that's as expected. But what wasn't expected is this kind of smudgy region we get down here in the hydrogen map, which looks like it contains a lot of hydrogen. So is that real from the experiment, or is this an artifact of storage, sample preparation, the vacuum system? So because we have the ability to map multiple elements in the NanoSIMS, if we look at the carbon map, things start to become a little bit clearer. We can see it follows the same distribution. So because we have resin over here, what has happened is that we have taken about half an hour to image this whole area. And in that time frame, when we're not imaging over here, hydrocarbons from the resin have diffused over the sample surface, bringing in hydrogen with it and complicating our analysis of hydrogen. So that is why we typically don't want to look for hydrogen in the NanoSIMS. We use deuterium. So we artificially introduce deuterium in our charging process, and we map that instead. And we assume that hydrogen and deuterium behave the same way in the microstructure. So the reason we like to use deuterium is that it has a very low natural abundance, only 0.015%. So pretty much any deuterium we detect in the NanoSIMS must have come from our experiment. We have introduced it. So if we look at the deuterium map now, you can see that that particularly smudgy feature over here has completely disappeared. We're just left with the hydrides, which must have formed from hydrogen we introduced during our experiment. So how do we get those isotopes into our metal? So we use two different methods depending on what alloy system we're using and the conditions that it would normally experience during service. So for our steel and nickel alloys, we did galvanostatic cathodic polarisation. So here we have our sample in a deuterated solution. So we're charging with deuterium in this case. For the zirconium alloys, in this case, they're being used as the fuel cladding for the uranium fuel in nuclear reactors. So what we wanted to try and do is to investigate their oxidation behavior and hydrogen pickup in simulated reactor conditions. So in a reactor, our zirconium tube is going to be sitting in water at high pressure and high temperature, such as these conditions here. So what we do with the zirconium alloys is we grow the oxide initially to a certain point. Zirconium has a very characteristic oxidation behavior while it goes through a number of transitions of fast growth and slow growth. And so we'll grow it to a particular point so we know whether it's just before one of these transitions or after a transition. And we grow that in normal water, first of all. After that specified time period, we'll take this zirconium tube out of that autoclave, place it into a different autoclave, this time containing water containing deuterium and also oxygen 18 in this case. And then we allow that oxide to grow for a further period of time. So the first bit of work that I wanted to talk about was conducted by a PhD student in my group, Dr. Yasser Abora. And Yasser's PhD project was really to try and understand what we could and couldn't do with the NanoSIMS. This has not really been explored in any great depth. Try and work out the artifacts, what is believable and what is not. And what we thought we would start with was alloy 303 stainless steel. Alloy 303 has a lot of manganese sulfides in it. And we thought, from reading the literature, manganese sulfides are supposed to be a location of hydrogen trapping. So we thought, great, these would be really easy to identify. We'd see hydrogen localized in or around them, and then we would know what we can and can't do with the NanoSIMS. So just an example of the first issue that we had to overcome with the NanoSIMS is something called the matrix effect. So here we have a series of images from the NanoSIMS: hydrogen, deuterium, oxygen, sulfur, which as expected shows a lot of sulfur in the manganese sulfides, and the secondary electron image, which was generated by the NanoSIMS. So if we look at our hydrogen and deuterium maps, we can see in this region here, this particular grain seems to show a lot of hydrogen localized to it. Okay, so we think, okay, why has that particular grain got more hydrogen than, say, this one, for example? Actually, this is just an artifact of the NanoSIMS. So what we're getting here is that this particular grain orientation is able to emit more secondary ions than an adjacent grain, for example. So what we do is we actually take a ratio of hydrogen and deuterium, and we generate another image. Okay, so this is now a ratio of deuterium divided by hydrogen. And what you can see is that all that grain orientation structure has now disappeared. We've left with a flat background. And what it has really brought out, and what we're actually interested in now, is where the deuterium is localized. So it's showing us the relative enrichment of deuterium compared to hydrogen in this case. So you can really see we've got a lot of deuterium enrichment in certain regions of our microstructure. And these are actually dislocation slip bands here. So the deuterium has segregated preferentially to these deuterium slip bands. And you can see the microstructure is quite complicated here. So that's all I'm going to talk about for the steel. This is still to be published, but it's just a nice example of this first issue that we found we had to overcome. The other issue, which we knew was probably going to be an issue, was the fact that, as I said, we don't have a cryostage on the NanoSIMS. And as I said, hydrogen in metals is very, very mobile. We were worried that we were going to lose a lot of our deuterium into the vacuum system before we could even analyze it. So what we aimed to do always was to try and charge our sample and as quickly as possible get it into the NanoSIMS under vacuum and start analyzing it. Now, attached to the NanoSIMS, we have what we call a residual gas analyzer, and it allows us to determine the composition of the vacuum itself here. So what compounds are in the vacuum itself. So we have incredibly good vacuum, but there are still certain things in there. So what we did here, and I'm not going to go through the whole of this graph, but I just want to point out this time point here. So this is where we introduced a deuterated sample into the chamber containing the residual gas analyzer, and you can see the deuterium signal shot up massively, dropped away over time, and then dropped massively as we removed that deuterated sample from that vacuum chamber. So this really proved to us that the deuterium is outgassing from our sample while we've got it in the NanoSIMS, so we have to work fairly quickly to do these experiments. So just to show that in a more visual way, we've got deuterium coming out of our charged sample. And the implication of this as well is that if we have an uncharged sample in the same sample holder, some of that deuterium is going to deposit on that surface, and we can never measure the natural isotope ratio as we would expect from an uncharged sample. So any areas of our sample that do not contain any deuterium, we will always detect some deuterium from there. So it has implications on our detection limit. In reality, what we think is actually this turned out to be quite advantageous for us, because if we charge a sample with deuterium, you're going to uniformly charge the whole metal surface. So if we had a cryo stage and we started imaging a uniformly deuterated sample, probably all we would detect was deuterium everywhere evenly. But by the fact that the freer deuterium that's not trapped has disappeared off into the vacuum, what we've been left with is an image which shows where the deuterium is trapped more strongly. So we're actually improving our contrast and highlighting the deuterium trap sites, which is what we wanted to investigate anyway. So the other work that YASA did was to look at a nickel alloy, which was 625 plus. This is a project in collaboration with BPICAM, so it's interesting for the oil and gas industry to look at this particular alloy. So the first thing we did was to look at this nickel alloy in the as-received condition. You can see it's got a very clean microstructure as shown by the secondary electron image. And if you look at our ratio image, you can see that we don't actually see any localized deuterium whatsoever in this sample. And that's because we have no deformation. So the next thing to do was to increase the complexity of this experiment and then look at a pre-strained sample of 625 plus. So we're now introducing some strain into our sample. We had a total deformation of 1.5%. And you can see from the backscattered electron image that we took just before we loaded this sample into the NanoSIMS, there are these clear localized strain regions around this grain boundary. And it's a little bit difficult to see on the projector, but you can actually see deuterium is now segregating to those localized strain regions as well. So once we've got a deformed microstructure and we've got dislocation slip bands, we start to see localized deuterium at these particular grain boundaries. So then what we did is we increased the complexity again, and we actually looked at a sample that was in situ charged and cracked at the same time. So we were charging it while pulling it and cracking it. So all the conditions are indicated over here. So here you can see we have a crack that's going through this sample, an intergranular to transgranular crack. We also do get some surface cracking from the electrochemical charging in this case. We can see we also have some sigma phase precipitates showing up just here. So again, the projector's not the best, but hopefully you can see we've now got deuterium localizing to dislocation slip bands. We also get deuterium localizing to the sigma phase, and you can sometimes see deuterium localizing to this twin boundary here. So what we've now got is mobile dislocations that are transporting deuterium with it as they are moving through the metal, and they're picking up the deuterium, and you're seeing these accumulation of deuterium at these particular regions. So one final region here. What we looked at in the previous image was the crack on the surface, but what we wanted to do was to try and find the real crack tip, because we thought this might be a region where hydrogen is strongly segregating too. Unfortunately, we didn't manage to find it after grinding away the surface. We tried to grind down to find the real crack tip. We couldn't find it. We should have gone to Tim with his X-ray CT to be able to find that crack tip, but we needed to work quickly, as I said, to get this sample into the NanoSIMS. But we did manage to find this interesting region here, where we've got a crack terminating just here and probably going out of the plane. We can see we've got a lot of grain boundary carbides running along here. We've got some cracking and some voiding and a lot of localized plasticity here. And again, we can see very strong deuterium localization to that localized plasticity and also to these grain boundary carbides here. So just to summarize what we saw from those nickel alloys, if we look at our in situ charged sample, while it was being cracked, We have our crack growing in here. As we do our in situ charging, we get, from the stress, we get these dislocation slip bands around the crack, and we get the hydrogen segregating to those regions. The hydrogen then starts being transported around by those dislocations, and it accumulates more strongly at those dislocation slip bands. And then the sample will crack further as it cracks into a region of hydrogen or deuterium enrichment. If we just have the pre-strain sample, we do get hydrogen accumulating around dislocation slip bands, but not to the same extent that we saw with the sample that was being cracked. And obviously hydrogen is causing a brittle failure in this case. So the other piece of work that I want to talk about was conducted by another student of mine, Dr. Chris Jones, and he was focusing on the zirconium alloys that are used in nuclear reactor fuel cladding. So as I said, these had to be oxidized in an autoclave, and they were oxidized in a deuterated rich environment. Now, the aim of Chris's PhD was to actually look at the irradiation effect on oxide growth, and I'll come on to that in just a minute. But he started off by looking at these alloys to begin with, and we found something that we didn't expect, which was we found these regions in the metal. So again, here we've got resin, the oxide, and the underlying metal here. And we could see very clearly in every sample we looked at these deuterated hotspots, essentially. So if we zoom in on one of those regions, it's very clear that they have a hole in the middle. And with some correlative imaging with SEM and EDX, we can identify that these are the secondary phase particles inside the zirconium alloy, so our iron and nickel and chromium-rich SPPs in these alloys. And so it's very clear to see that the deuterium appeared to be segregating around the edge of these, and with some complementary modeling, we could prove that this deuterium was localized to the matrix surrounding these SPPs associated with the strain field. So this was something that had never been observed before, but it's really important if you're trying to understand hydrogen pickup in these nuclear alloys that you know where the hydrogen is going. And so people did not know that this was a location of hydrogen trapping in zirconium alloys. So the real aim of Chris's project was to look at the growth of the zirconium alloys after irradiation. Obviously, these zirconium alloys are going to be subjected to a lot of neutron irradiation. Does that have an effect on how this oxide grows? So Chris had a whole matrix of samples, some which were not irradiated at all, and some that were irradiated to various levels of displacements per atom. And this irradiation was performed at the Dalton Cumbrian facility using proton irradiation as a proxy for deuterium irradiation. So on the left-hand side here, we have a sample that was grown for, the oxide was grown for 131 days in normal water, followed by 40 days in our oxygen-18-rich environments. This had no irradiation, and what I want to demonstrate here is how we've managed to start to move to be able to map over larger areas of the sample. So all of this is actually one continuous piece of oxide. This image here attaches to the side just over here. So actually, in some cases, we've managed to image over millimeters of length of sample of oxide. And so we're really now getting a much more representative view over the oxide. And what became immediately apparent is that although zirconium undergoes these transitions, and you can see that in the weight gain behavior of these zirconium alloys, people thought, okay, that maybe the whole alloy transitions at the same point. But what we can show with the NanoSIMS and with these oxygen-18 labels is that things do not always happen at the same time. So where we have incorporation of oxygen-18, which is this pink line along here, the metal oxide interface, that is oxide that has grown in those 40 days that that oxygen-18 label was present in the autoclave. So you can see here that the outer oxide of this region here must be completely porous to the water. The water is able to penetrate through that oxide and react directly with the metal underneath. And so this has gone through a transition. But if we look at this adjacent region here, we can see that this has not incorporated any oxygen-18. This bit of oxide here, and actually this bit of oxide just over here, has not yet undergone that transition. So we can see individual events happening in some cases where you can see the penetration of the oxygen-18 and spreading out of the oxygen-18 along the metal oxide interface. So we're starting now to get sort of temporal information from our NanoSIMS imaging. So you wouldn't be able to determine this just by looking at the structure of the oxide. That oxide is probably similarly, very similar structure to what's above it, and chemically identical. So by using the oxygen 18, you can actually pinpoint exactly which bit of oxide is growing at any particular point in your experiment. So the other image here is after 0.75 displacements per atom. You can see now the oxide is looking a bit of a mess. We've got a lot of cracking along the middle here. And we can also, again, look at pathways of which oxygen 18 is penetrating down through our oxide. So you can see we've got these large cracks just here. And on these crack tips, we can see oxygen 18 is being able to penetrate from the water out here through these cracks, and it's growing new oxide and heading off towards the metal oxide interface. So we can look at pathways. You can see another pathway probably starting to form here of this oxygen 18 penetrating through this protective oxide down to the metal oxide interface. So just to conclude then, so I've demonstrated how the NanoSIMS has been able to successfully image hydrogen trap sites in a range of different metals, something that is very difficult and very few techniques can actually achieve. We can get some really unique information by using isotopic labeling. So we've used deuterium, oxygen 18, but you can use carbon 13, nitrogen 15. So you can get that temporal uptake indication. You can get that snapshot of what is happening at a particular point and see where in your coating or where in your oxide a particular element is incorporating. So I think there's a lot of potential in corrosion studies by exploiting the high resolution that we can get with the NanoSIMS. We get high sensitivity to look at trace elements. This isotope specificity opens up a lot of possibilities, and also the option to detect light elements, lithium, boron as well, which can be really interesting. So I'd like to finish by acknowledging specifically Yasser and Chris. They did all of the work that I presented today. EPSRC for funding Chris and Yasser's PhD, and also the BPI-CAM for co-funding Yasser's PhD. So with that, I'm happy to take any questions.
Thank you very much, Katie. Any questions for Katie? Well,
you mentioned that the lack of a cryo stage is one of the limitations. Is that a fundamental limitation, or is it simply that it hasn't been made or you haven't got one?
So the instrument manufacturers say that they don't see a need for it, even though all the biologists keep saying we need a cryo stage, we need a cryo stage. Right. So basically the instrument manufacturers haven't done it. Someone has built their own, which is yet to be published any data from it, so I don't know how good it is.
Okay, so it is technically possible.
It's technically possible.
That would be very interesting for hydrogen, certainly.
Exactly. I mean, the biggest issue is that the sample stage is at 8 kV, so your whole cryo stage has to be at 8 kV, so that offers some challenges, but other SIMS instruments have been able to do cryo stages.
It just occurred to me that, I mean, what happens if you take a relatively large thermal mass and chill it before you put it in?
Yeah, we haven't tried that. We could try and put in a cold sample and see what happens, but we've got to be very careful with the vacuum system. And one worry is that if you did have a sample in cryo conditions, it would probably get at all of the hydrogen in the vacuum system, and all of the hydrogen in your vacuum system would sit on the surface, and you'd have to dig through that before you get to your real sample.
Everything would change thermally as well, I guess, Thank
you very much. Any other questions? Great. Andy, sorry, Tim.
Thanks, Katie. I was just interested, as I always get asked, it's always people need more and more resolution to see these things. And it struck me from some of those images where you see hydrogen associated with slip bands or particles, you still want to go that step further to say, is it like on the interface? Is it just one side? Where exactly is it? I was wondering, are you able to use modelling to sort of predict like how that should look and therefore sort of improve the resolution or sort of know where the hydrogen's coming from more accurately? Yeah,
I mean, for the hydrogen in the SPPS and zirconium alloys, we did use modelling because we weren't entirely sure if it was, I mean, you could see the hole in the middle, but we still weren't sure that there wasn't any deuterium in the SPP itself, or whether it was purely around the edge. So the modellers did a lot of work to look at where hydrogen would favour sitting, and we concluded that it was in the matrix around, and that did match up with the NanoSIMS data. So we have done that, and we could, extend it to dislocation slip bands. I mean, pushing the NanoSIMS resolution further for hydrogen is quite challenging. It all comes down to how many hydrogen atoms you have in the volume that you can sputter and how many can you collect.
Yeah, so. Thanks.
Stuart?
Hello again. Yeah, well, it's just a quick question really about, since you're sputtering all this rubbish into the vacuum chamber, is that going to cause a problem with contamination?
Yeah, so that's one of the things we did look at actually, was you do get deuterium sitting on your lenses, so it takes you a while to clean off the lenses. It's not our biggest contamination issue. Our biggest contamination is the outgassing, but it's something we did look at for sure.
Thank you. Katie, I've got a couple of questions for you. Why are you using 2 ions? Why not just use 1 ion and then an electron gun to flood it to get the charge balance?
You mean the cesium and the oxygen
Yes,
source?
cesium and oxygen source.
Okay,
Yes.
so the NanoSIMS has a very specific setup of its lenses. So if you have a positive primary ion beam hitting the sample, you can only detect negative ions coming off the surface. So we have a positively charged cesium source and a negatively charged oxygen source. So depending on whether the ion that we're interested in detecting is more likely to come off as positive or negative, will determine what we choose for our primary ion source.
Okay.
So hydrogen typically comes off as negative ions. Things like sodium, potassium, calcium will come off as positive, so we have to switch sources. So there are some limitations on what you can do simultaneously. You can't do fluorine and calcium at the same time because they have very opposite polarities.
Right, okay, no, that's obvious, yeah. And the other one was, why no molecular information?
Okay, so there is a SIMS instrument that is much more gentle to the surface. So we kind of talk about them as a digger and a tickler. Okay. So the time of flight SIMS instrument is known as static SIMS. That's much more gentle to the surface, and it will lift off bigger molecules from the sample surface, but it doesn't dig as much, and your sensitivity is not as good. Whereas with the dynamic SIMS instrument, which is what the NanoSIMS is, you use a very intense primary ion beam to really dig down deeply, get a lot of secondary ions off your sample surface, but in the process you basically smash all the molecules up, fragment them down to individual ions, essentially.
So you literally are breaking every bond.
You're breaking almost every bond. We get very small molecules, but not much more than 3 or 4 atoms.
Because in my out-of-date thinking about these things, I've always thought of XPS as being the sort of atomically sensitive surface technique, and SIMS as being the molecularly sensitive. Yeah. But I understand entirely. That makes sense. The other question was, in your ratios, you talked about deuterium. In some of the graphs, you talked about deuterium. Yeah. But you actually had them labelled as oxygen 16, deuterium to hydrogen 2. Yeah. Why?
So this is some very specifics of how we found when we were working out what NanoSIMS can and can't do. In some cases, we found it better to actually image the deuterium in the passive oxide layer that had formed on the nickel and steel alloys. Okay. So then the deuterium is incorporated into the passive oxide, which may only be a few nanometers thick. So there, it's actually, you get more signal by imaging OH ions or OD
okay, so
ions.
you are actually limiting a molecular species.
Yes, yeah.
Right, okay.
So as you go through the oxide, you get more of the OH and OD ions. Then as you go into the bulk metal underneath, it's better to switch to use hydrogen and deuterium. Okay. So there was some artifacts that I didn't go into because it was a bit complicated for a half-hour talk of what works best in what situation. Yeah, no,
it's a little sleight of hand, so to speak. No, I'm just trying to think about the chemicals. I mean, OH is what you're actually seeing, not deuterium. Yeah. It is localization of the deuterium.
Yeah, we found it replicates very well what we see in the bulk. We just get better signal from it.
Okay, great. Thank you very much. That's very helpful. Any other questions? Sorry, Richard.
Yeah, it's a question from a polymer scientist who loves deuterium. We always start out with the assumption that hydrogen and deuterium are the same, but there are some subtle things about in the way their thermodynamics operates because of the 0-point energy difference and that kind of thing. Is that relevant at all in metals, or can we just forget about it?
It's something we considered, but to be honest, we were hands are kind of tied by having to use deuterium. When we do map hydrogen, it pretty much looks exactly the same as our deuterium map. So there is some confidence that we are actually detecting the same thing with both, and they are behaving similarly. I'm not sure if we'd really be able to detect the difference with the NanoSIMS in terms of sensitivity. You know, it's probably not a big difference that we would be able to detect in terms of where hydrogen is migrating to, for example.